but we will turn to something different because we are planning to describe a deep learning and a high data availability and the necessity of having a mathematical background for it. Because of course we are aiming to a situation where we wanted to use AI as a service that we can join the website and use it. However, still it is wise to know the background of the problem, right?
Yes, and I'm really excited about this topic and about this presentation because we know that deep learning is a pretty wide and complex field. And I noticed that there is something about how to make it easy. So I'm really looking forward to it. And now,
so let me invite Josef Nový from Czech Technical University and CERN to present what is easy, what is hard.
Thank you for the introduction. So in my presentation, I would like to take you from beginning of the artificial intelligence to the current landscape of deep learning. Basically, the beginning of the artificial intelligence can be set as 1943, where the publication about perceptron appeared by McCulloch and Phil. The development of the artificial intelligence actually stopped, or interest in the development stopped twice during this time. First, it was between 1969 and 1974, and second time it was between 1998 and 2006. Those periods are called neural winter, and they were caused by several problems. One of them was computational power. Another datasets which were not easily accessible or not present at all, and also problematic training of the networks because the theoretical background was not there. Those problems correspond nicely actually to the creation workflow of the artificial intelligence or neural networks, which are get data. So you have to first have the data on which you want to train your network. Then pre-process data. Your data have to be prepared for the model to accept. And this is true not only for the supervised learning, where you have to label them, but also for unsupervised. And then, of course, the creation, training, and verification of the model itself. All those steps needed some development in three different fields. First is network architecture and training algorithms, which we can basically put into the field of theoretics in the artificial intelligence. Then hardware, which allow us to process and train larger models and larger datasets, and tool sets, which allow more people to get involved in the artificial intelligence, as they make it easier for people to access those resources. We also have some current challenges which were already mentioned in previous block, actually. And it's not only misuse of deep learning, but also fast development of the large models without appropriate alignment. So now for the beginning of the neural networks. It all started by basically inspiration from nature, from neuron. Simple perceptron was created, as I said, in 1943. This still usable actually for many applications, and good for this is that it's possible to train it also manually. You can use Boolean algebra and prepare your neuron without any need for processing of the data. It's small and easily understandable. I can show you simple code in both C++ and Python. I will also show codes for more bigger models. Usually you will see that C++ is a little bit longer than Python. Here is also really important mathematical equation for the perceptron, which is used for calculation of the response. So just keep in mind how long the code is and how complex is the first network. It's not that big. But if we go further, we are getting to multi-layer perceptron, which is actually still key part of many architectures as last layers in the models. It is very nicely usable mainly for classification, but also game AI, anomaly detection, medical diagnosis, image and speech recognition, many fields where you can use this layout. But the problem is both with training and complexity of the problem, because it involves several layers of fully connected neurons. So each neuron in one layer is connected to each neuron in next layer, which means that if you want to analyze, picture, full picture or video, you need a lot of variables that you have to train, and this can be a problem. I just hint a thing that you can try. You can try at Playground TensorFlow.org to design some multi-layer perceptron to test how it behaves. You can change how many neurons you have in each layer, what inputs you have, and also which functions are used in the neurons. And then you can see how it teaches classification problem. Okay, so here we have code for multi-layer perceptron. You saw that it grew a lot from the single perceptron, but the code is not that bigger, thanks to usage of tools and libraries to help us implement the bigger model. Here we have, for example, again and NumPy in Python, respectively. So we have much bigger network, but not that bigger code. And now, when we want to go to even bigger and more complex networks, we actually almost need to use some bigger frameworks and toolsets, like TensorFlow or Keras, Coffee, or I know MXNet. It depends in which language you are developing, and they are not on the same level of abstraction. For example, TensorFlow is lower level, Keras is higher level. But still, it helps us implement bigger networks, mainly because you have prepared training algorithms for the networks. So, and what kind of networks we actually can use in such frameworks? In the past years, many different architectures emerged for different tasks that the human need to solve. You probably will know, or at least heard, something about convolution networks, which are typically used for image and video processing, and are very nicely usable thanks to specific way that they are processing data. They are not fully connected, so you can have less parameters than in the multi-layer perceptron, and they are extracting features from the image, based on which you decide the class or classification of the image. Here is an example of some CNN network. You can again see that it growed a little, the code, but still it's not nearly as complex as it could be if you wrote it in just simple way as was in the multi-layer perceptron example. Another examples of those architectures are, for example, recurrent neural networks, which are used for signal, speech, and time series, or autoencoders, which are highly used for cleaning noise from the images. But as I said, many architectures appeared. Here are several other examples, like generative adversarial networks, which use two networks, one that generates images, one that decides if they are true or not. And this way, the first can be trained to generate, for example, picture based on some prompt, or actually they can be also used for detection of anomalies in, for example, network transfer. So you can in advance stop some threads or exchange faulty equipment ahead of the actual failure. And of course, I have to mention in between new architectures also transformer networks, which are a big thing now with ChatGPT. Another thing that helps make the deep learning easy is availability of free datasets. This is actually a huge advantage because before, I think maybe half of the time that you spent on preparation of your use case was preparation of well-prepared dataset, labeled data, because you need a lot of things, a lot of pictures. For example, if we stay in the picture classification field. And thanks to the free dataset, you can have some head start in this. Second part of it is availability of pre-trained models. Before I talked about the architectures that are available and implementation of these architectures are available in pre-trained models. This is also very useful for start, because you don't need to teach the whole model, you just teach the last layers. Then you can use even the big model with a lot of variables for your application and don't need really some fast GPU-based server for teaching. You can teach it on smaller machine or in some virtual environment, and it helps a lot with smaller projects. And now we are getting to really interesting part, AI tools. With this, we are getting to the place that you actually don't need to interact directly with the model or the neural network. You don't need to teach it anything. You just give a prompt, which is actually also important knowledge to have. As you have to learn how to put a correct term in the Google search or anything else for searching, any other searching engine. It's also important to teach how to formulate your requests for the AI tools, like ChatGPT or image production, things like Midjourney, or I think now it's Adobe Firefly. It's the new also AI tools for pictures. Here I put some example of the image produced by the Midjourney and the prompt that was used for it. We can see that the pictures that it can produce are really nice, and you can produce many more styles. What is the most interesting for me as a software developer are Copilot and Code Whisperer AI tools, with which we actually getting to the point where AI helps to write another AIs and the code. It helps a lot and make the work of developer much more efficient, let's say. Okay, so that was all for development of the field, from perceptrons to landscape, deep learning landscape as we have now. And I would like to talk now about practical usage of deep learning, what we have at our university. Basically, the variety of use cases is really huge now, partly because development of the frameworks and also the free data sets. People can start with a nice project and get the good result really fast. But we should not forget about need for some background knowledge if you want to get the perfect results. Because for example, all the inputs in the networks are in some way transferred to vectors or matrices and tensors. If you want to teach your network, you always will encounter training methods. So it's useful to know what variables come inside and how these numerical methods are working. And of course, statistic and information theory is quite useful. As always, you have to define loss functions or some other way to describe your result that you want, or evaluate if the response of the system is good for you or not. Here we have some examples of smaller works, actually of the students. For example, the classification of architecture types, and also heat maps of the pictures, which show you what part of the picture is important, or architecture is important for the style. It used the convolution network for this, and also some transfer learning method. This is also a nice small project as a final exam of computer course about usage of AI for a simple football game. Actually, the student get to the point where it was almost impossible to win against the AI. So nice result. And one on which I am personally really proud is application of neural networks in augmented reality. Because normally when you calculate depth of the image, you use two cameras. But with usage of the neural networks, student was able to get deep depth information from one camera and one image. And on the pictures, you can see comparison between two different models and the source image. Another nice application is utilization of convolution network for object recognition in the augmented reality. With use of Unity and TensorFlow, student was able to detect mouse or other objects and put the information about the objects from Wikipedia next to it. So it's proof of concept, let's say, for augmented reality. The neural networks or deep learning is also highly usable in, for example, healthcare. Here we see example of usage of segmentation for help with diagnostic creation on vertebrae and discs. Basically, model segment the spine, and it can then measure distances between vertebrae. It can nicely help doctors to make a more precise diagnosis or help to create a diagnosis. It's not the only place where you can use deep learning actually in medicine. It's also nicely usable for example, cleaning of the images of the noise, make the scanning process on MRI or CT faster because you can upscale the image or clean it. But we have to take in account that it's always better to use it as support and not direct diagnostic tool. It's better to use it as help and final thing. We also using the deep learning in CERN, in Ember experiment, where it's used for particle classification. Actually, CERN also developed its own toolset for machine learning, and it helps a lot making fast decision and reconstruct tracks, detect anomalies in detectors, and many other stuff. So for conclusion, I would like to pinpoint that thanks to simultaneous development of both hardware, theory, and tools, the models grow a lot, but the complexity of code and usage of the networks is not that big. It didn't grow that much. So it's easy to get good results from AI. But I think it's impossible to get perfect results. Neural networks are always in some way about some statistics, probability that the response is true. And it's highly usable to have some mathematical background and theoric knowledge of the networks, how they are working, how they are trained, and so on. So if you want to use them in the full potential, you should learn some background things. And what's next in AI? That's probably a big question for many speakers today. So that's all from my side.
Thank you very much for your presentation. It was very nice. I mean, I have a really quick question that follows up, because I heard that this CERN project, they're looking for the particles. There was actually a competition. I don't know whether in this particle experiment that many teams were competing in sense of winning the best I don't know, prediction or classification?
Not this one, but of course the particle identification is a big thing in all the physics experiments. So many teams are working on similar things. Yes. And in physics, you always try to have actually more teams that are not directly cooperating, because you want to evaluate your final product to have more, let's say, not related responses. So if two are true and one not, you can still decide which one is true. Even in the physics experiments itself, it's highly usable to have more experiments that are doing the same thing, and they can compare their results.
Yeah, it could be complete. And maybe a quick follow-up. I mean, are you sometimes facing that there are too much data in sense of computational complexity or something like that?
It's always a race between the tools, hardware, and amount of data.
Or something that you are even not able to compete. That you were really facing some limitations of yours.
Yeah, of course. Now it's more matter of if you get money to buy the proper hardware, then that it's not available or not possible at all.
Okay, thank you for deep dive into the complexity of neural network. It looks like that you somehow skipped that easy part. But generally, as I saw the depth-based research, which is based on AI as well. This could be a huge game changer to many industries, including automotive. So do you continue on this research to take or to estimate somehow the depth from single photo?
The student is working on the stuff still, but we'll see. We actually have also collaboration with another faculty, and we are also partially looking in working in automotive. So we have many projects and try to combine actually the outcomes of the smaller one to some bigger one and compare it with another ways how to get, for example, that information. It's always good to compare, for example, this neural network from single photo with traditional way of getting it from two cameras. And also, especially in automotive, you always try to get the information from more than one source to have certainty that the response is good and correct.
Yes, exactly.
I may be asking a different question again about the data, similar as before, but the opposite position. So what if the data, if you don't have so much data, data are uncertain, you know there are many exogenous variables you don't know about. Are you facing problems like that?
Yes, and typically they are solved by simulating the data. You prepare a mathematical model and use, for example, Monte Carlo to generate data what you want or need as basis. Then try on the real data. If they are not enough, you still have a way to teach your model, and then just evaluate or validate that the model is working good with.
Okay, so that's the one. What about this including the uncertainty in the neural network? Something like I'm heading towards this fuzzy networks and stuff like that.
Yeah,
maybe not
personally. I didn't try. So
yeah.
But for example, we now trying to prepare some process of producing also for the automotive automatically labeled stuff. So.
And
I think that's
okay.
All from our side.
Maybe one question again. This about the speed, because sometimes we heard the speaker before. It's very important to have a quick answer, right?
Yeah.
So, is there applications where the requirements for the answer is to be really quick, and you need to tune it somehow.
Especially in physics, it's true. If you are at the physics experiment, and you need to just choose what you take because you don't have enough computer resources to record everything. Usually, from the experiments, you have to choose what you want to record. There, you can use fast neural networks to decide what is interesting, what is important, and record just this.
And you create the next step based on the decision in the previous step. Oh, that's very nice.
Okay, I now notice that we have some
Okay,
more
yeah,
time.
maybe.
So maybe one more question. Could you a little bit more give us the idea how about using AI in the medicine? Because we saw some photos from MRA.
Yeah. For example, in MRI, you can shorten the time the patient is inside, and you get more noisy picture. But with AI, you can clean out the noise and get the, let's say, similar quality as with long period of data taking with smaller one, which is especially usable if you need to scan something movable, like heart or something like that.
Yes.
Another field where you can use it is the segmentation. You can segment the bones and organs, and it is also quite usable. You can find some part of the picture which should not be there. It's also usable.
Yes.
Or automatically search for cancer or something like that in the pictures. So use cases are there, many of them, and it's more matter of not enough people than not enough topics, let's say.
Yes,
Exactly.
I see.
And of course, big thing is that it's a kind of safety application. So you have to take in account that you have to be really careful about the responses of the network.
Yes, it means that there must be someone who always validates the output
Yes,
and
exactly.
decides whether it is really right answer to the question or not. But on the other hand, we already mentioned the problems and the issues which should we somehow solve or mitigate when working, for example, with the data, because the photos or the results from the scanners are still somehow tightly related to the people, and we need to take care about this.
Yeah.
Okay.
So in the end, there will be doctors with many recommenders to just deciding which is true. Okay, we are not only out of people, but out of time. So thank you very much for a great presentation. It was a nice contribution. Thank you.
Thank you.
Thank you.